In a previous discussion, I had talked about the reflection of light off a plane mirror, not P-L-A-I-N, like plain yogurt. Plane as in flat mirror. The sort of mirror we would use as a dressing mirror or the mirror that's above the sink in the bathroom, a mirror that is perfectly flat. A convenience of that, from an intellectual standpoint, is that the flat mirror makes it very easy to figure out where the rays of light will go, because we've learned the simplest rule in all of physics, I think. That's an opinion, not a fact, but I think I'm right. The law of reflection, which says that the angle of incidence is equal to the angle of reflection. So if I consider that I have an object here on the left that is going to be reflected in the mirror, there are an infinite number of rays of light that go to the mirror. So you don't want to try to consider it all at once. Your brain can't handle that. So you pick a few rays that will give you the idea. In this case, I only need two. The first ray that I've drawn goes from the object here to this dotted line that I've drawn through the middle of the mirror horizontally. It's just a coincidence that it happens to correspond to the end of this lollipop object that I've drawn. But there it goes toward the mirror. When it hits the mirror, it reflects in such a way that the angle of incidence is equal to the angle of reflection. So it's a matter of geometric construction for me to see where that ray goes. If I choose a ray arbitrarily at a lower angle, it goes to the mirror, and for my convenience here for the lower reflection, I've dropped in a dotted line there. So I can see that the angle of incidence is equal to the angle of reflection, and there it goes. Now what happens in terms of the visual effect that is perceived by the human being who's looking into the mirror is that the human eye can only create visual perception from rays that are spreading out. To describe spreading out, I'm going to use a bit of a fancier word, diverging. To diverge means to separate. And these two rays that come bouncing off the mirror and toward the eye here, this is my cartoon representation of an eye. You see eyelashes and an iris and a pupil. Looking at it, this eye sees divergent light. In order for the human optical sensory system to create an image in your consciousness, there must be diverging rays. And your brain does a thing that is, I don't know, let's not call it foolish, but a bit mistaken. Your brain, in its perception, assumes that those rays traveled in straight line paths, despite the fact that those paths lead behind the mirror into the wall. I've made them dotted lines on my diagram because it seems to your eye that the light came from the far side of the mirror. Of course it did not. In the lingo of optics, we say that the image that you see in the mirror is a virtual image. And the distinction is that the light does not come from there. If you are on the left side of the mirror, and there's the lollipop, when you look directly at it, not its reflection, light comes from it into your eye and you perceive it. That is a real image. And you say, oh, because it's the real object and this one's the fake one. No. It's real because the light actually comes from there to my eye. This image is virtual because the light does not actually come from there. Now, there's a little bit of geometry to this. The math is not interesting. You know I like to turn things into equations, but what am I going to do? The distance that the virtual object appears behind the mirror is equal to the object distance in front of the mirror. So the person inside the mirror appears the same distance. We talked a bit about that it seems like it's left-right reversal, but it's really front-to-back reversal. And that's the discussion of plane mirrors, flat mirrors. Well, what happens if the mirror is not flat? And that's my interest for today. I want to investigate a curved mirror. You say, why would a curved mirror? My bathroom mirror is flat, my dressing mirror is flat. Well, in your everyday life, you encounter curved mirrors. You just haven't necessarily realized it, and I'll hopefully point out some of those instances to you. I'm interested today in what are called spherical mirrors. A spherical mirror is called spherical because it is part of a sphere. In this introductory diagram, well, I'm just giving you the terminology of spherical mirrors, I have indicated a circle here, which is the entire sphere. The mirror itself and here's an example of a spherical mirror, the mirror itself is only part of the sphere. Do you see what I'm on about? The mirror itself is called spherical not because it forms the complete sphere, but because the arc of the mirror is cut out of a sphere. Now, this spherical mirror that I hold in my hands here is quite large. Imagine completing the sphere. It would be very big indeed. I don't know exactly what the radius is, but the sphere would be enormous. And of that enormous sphere, the mirror itself is only a part. So some terminology here. There is a dotted line that is drawn here from left to right that goes straight through the center of my curved mirror, my spherical mirror. It's called the principal axis, not only for spherical mirrors, but in all of the discipline of all of the discipline of optics. You typically find yourself drawing a line across your diagram, and that line is typically referred to as the principal axis. I have my eyeball here, which is the viewer, the human being who is going to perceive the interaction of light with this mirror. The object that I put in front of the mirror is most sensibly called the object, and the perceived light by the observer, the viewer, is called the image. Now, a sphere, of course, has a center, and I've indicated it here on the diagram. It's called the center of curvature of the mirror, and I've labeled it C. Very sensible. The vertex of the mirror, that is the centermost point of the mirror, labeled here V, the vertex, is the radius of the mirror away from the center of curvature, because from the center to the vertex of the mirror would be the radius. Halfway between the vertex and the center of curvature is a very special point called the focal distance of the mirror. Now, it's halfway between the center of curvature and the mirror itself. That seems a little bit arbitrary, but it has a very important special property, the focal distance. And it's critical to understanding the way that the mirror is going to behave. Here is the very simple rule, and you don't have to memorize it immediately because I'm going to use it over and over and over again. When I have a spherical mirror, like this one, for example, if I have a ray that comes in from the left here, parallel to the principal axis. Now that would be coincidental, wouldn't it? I mean, there are rays of light everywhere, and I get to choose which rays of light I consider. So I consider a ray of light that is parallel to the principal axis. When that ray, parallel to the axis, strikes the mirror, it will reflect according to the law of reflection, such that the angle of incidence is equal to the angle of reflection, but the normal to the mirror, that is the line perpendicular to the mirror, changes depending on where you are in the mirror. It always goes toward the center of curvature, but that perpendicular changes. So when my parallel ray of light comes into the mirror and reflects, it reflects according to the normal at that location. Every parallel ray, no matter how high or how low on this diagram, every parallel ray that reflects off the mirror reflects through the focus. That's the special feature of the focus. Light that goes into the mirror is reflected to the focus. And the term focus, I think, in our minds implies a kind of collection, like all the rays would go there. So if I had a mass of parallel rays traveling in here from the left, they would all converge on the focus. And that fact of spherical mirrors is going to make it possible for me to work out all of the special effects. There are two kinds of spherical mirrors I'm going to consider. There's a kind of spherical mirror, like the one that is on the screen at the moment, that is curved inward, like this one. It's called a concave mirror, like a cave, like bent inward, I guess. A concave mirror. And there's a second kind of mirror, which is a convex mirror. This mirror is mirrored on the other side. Its concave side is just the buff back of the mirror. The reflective side is on the outside of the curvature. This is called a convex mirror. I'm going to talk about both, and I'm going to start with the concave. Here is my first example of a concave mirror. I have to draw many of these diagrams because what I'm going to do is I'm going to put the object, as I have here, outside the center of curvature and see what I get. I'll then put it at the center of curvature and see what I get. I'll then put it between the center of curvature and the focus and see what I get. I'll then put it inside the focus and see what I get. It turns out in each one of those cases, I get a different result. Now, as I mentioned, my ray diagram, once it's complete, is very, very busy. So have a little patience while I explain each one of these rays and how they're constructed. First, I start from my object, and although there are an infinite number of rays, I'm going to draw a select few. A ray that leaves the object parallel to the principal axis and strikes the mirror, this ray here at the top of the diagram, reflects and travels through the focus. There it goes. And so I've drawn that one ray. If you draw your diagram like dynamically, one ray at a time, that's not enough to locate where the image is. So I have to draw another ray. Well, the rule that a ray that comes in parallel goes through the focus works in reverse. A ray, here the lowest ray on my diagram, that goes through the focus comes out parallel. A ray that goes to the center of the mirror is symmetric above and below, because when you hit the center of the mirror, the normal line is the principal axis. So that ray reflects. Notice that all of those rays have converged at a particular location. There's no physical thing there, but when the rays go through, pass through that location, afterward they are divergent. I have put the viewer here. The viewer sees divergent rays, and the mind in its perception follows those rays backward to the image. Unlike the plane mirror demonstration that I just did, the light actually comes from that image. The light rays travel from where that image is to the observer. This image is real. It's a real image because the light actually comes from there as it diverges to the viewer. Object, image. This image is described by 3 criterion. It is real because the light actually comes from there. It is inverted because it's upside down. And it is reduced because the geometry of the rays implies that it is smaller. So what I've discovered by drawing my ray diagram is that when the object is outside the center of curvature, I get an image that is real, inverted, reduced, and as it happens, between the center of curvature and the focus, although that's not, I don't consider that to be one of the identifying criteria because I can calculate that. For my next example, I'm going to draw rays again, but I'm going to move the object to the center of, oh, I forgot to mention, pardon me. Heaven forbid. Some context here. Why do I care about these rays bouncing off a curved mirror? Well, this type of mirror is inside of a camera or a telescope. This is the concave mirror that came off the end of the barrel of a reflecting telescope. So there would be a cylindrical barrel coming off of this, and you point up in the sky, and the starlight comes into the telescope, and it reflects off of this mirror. Because the stars are very, very far away, all of those rays come in essentially parallel, which means they all reflect and go to the focus. So inside the barrel of the telescope, the sensor that detects the light is suspended right in front of the mirror, exactly at the focal point, and all of the starlight comes to the sensor. Now, that of course would mean that the sensor itself blocks some of the starlight. So when you get an image from a reflecting telescope, there's like a black circle in the middle where you didn't get any starlight because the device itself blocks the starlight. But rays that come in parallel, reflect off the mirror, and then to the sensor is a practical application, because certainly if this is my mirror, the stars are well outside the center of curvature. And so this would be an example of that. And the same mirror configuration is often taken advantage of in photographic cameras, producing a real, inverted, and reduced image. Now I'm going to go to the center of curvature and draw my rays again. I'm going to draw the same rays. A ray that goes in parallel goes through the focus. A ray that goes through the focus comes out parallel. A ray to the center comes from the center, symmetric above and below. And what I discover is that at that special point of putting the object right at the center of curvature, is that the image is right at the center of curvature, but inverted. When the observer is looking at this image, the light actually comes from the image. This divergent light is coming from the location in space where the object is. This is a real image, and it is inverted, but it is the same size as the object. When the object is far away, the image is very small, but as the object comes closer, the image gets larger and larger and larger until when the object reaches the center of curvature, the image height is inverted, but the same height. So their size appears to be the same at that instance. This is a special case, and I'm not aware immediately of any practical value that it has, but there's a kind of trick that gets done. It's almost like a magic trick, where you take this spherical mirror and you set it up, and here you place, I'm going to draw on my slide just so you can really see what I'm doing. You place a box that your audience can't see in. And on the top of the box, you put a light bulb, and you screw the light bulb in and it lights up. And underneath, you have an identical socket, and you have a light bulb screwed in there. And both light bulbs are lit, but your audience can only see the light bulb on top. It's pretty wild when you see this done live. I'm sorry that I don't have the apparatus. And I tried to find a picture on the internet of it, but I didn't find one that was adequate. Ultimately, I just have to build the thing. But what you do, you say, oh, look, everybody, there's a light bulb. And then you unscrew the light bulb and take the light bulb away, and your audience still sees a light bulb there. Because the image of this light bulb forms where the original light bulb was. And people get freaked out because they can still see the light bulb. You just removed it and the light bulb is still there. But it's an optical effect. So I've seen this used as a trick, but it really is the special case of putting the object at the center of curvature of the mirror. Next case is going to be putting the object between the center of curvature and the focal length. And you see, it really changes things. Same rays though. A ray that goes in parallel goes through the focus. A ray that goes through the focus comes out parallel. A ray to the center is symmetric from the center, and my viewer sees divergent light that comes from the actual point. That is a real image. It's still inverted, but now it is magnified, larger than the object itself. So we say that that image is magnified. This kind of reflection is used in some projection systems, like movie projection. I'm doing the same ray tracing every time. I'm just getting a different result because of the position of the object. Parallel ray to the focus, ray through the focus parallel, ray to the center symmetric, and I end up with my image location based on the geometry of those three rays to locate the object along the axis. Well, now I guess I'm going to take the object and put it at the focus. When I put the object at the focus, a very strange thing happens. A ray to the mirror goes through the focus. A ray to the center goes symmetric. Now, I'm going to alter a little bit. I can't go through the focus. That's straight. I missed the mirror. But it is true that a ray that goes straight to the mirror and hits the mirror perpendicular to the mirror at that point turns around and goes away. The point is this. When the object sits at the focus, the rays that exit are parallel to each other. The rays are not diverging. So the human perception can't make an image out of that. No image is created when the object sits at the focus. No image is created when the object sits at the focus because the rays that come out of the mirror come out parallel and therefore do not diverge. One practical, I'm calling this a special case, but there is a practical use for this. Your car has headlights on it. Now, for the headlights to be most effective, you want all of the light of the headlights to go forward. That is, you want to create a beam of headlight. So what you do is the back of the headlight is a spherical reflector, no matter how fancy the front of the headlight looks to make the car look fashionable and interesting and desirable. but the back of that is spherical. So you put the light bulb that produces the light of the headlamp at the focus, and then all of the light from that light bulb that travels to the mirror in the back comes out parallel to the axis, a beam of light, which is then adjusted in focus to appropriate distance in front of the car to make headlights most effective for driving in the dark. So there, you're not trying to form an image, you're trying to form a beam, and putting the source at the focus can do that, creating a beam of light. One last option I have is to put the object inside the focus, and a remarkable thing happens. If I put the object inside the focus, a ray parallel goes through the focus. A ray to the center goes symmetric. A ray straight at the mirror bounces straight back. Here's my viewer tracing those rays backward, and just like the plane mirror, those rays get traced backward to a position that is behind the mirror. For the first time in all of these demonstrations, I've created an image. The light doesn't come from the image. This image is virtual, doesn't actually exist. It's human perception that created the image. Also, my images have been inverted, inverted, inverted so far, and now I've got an image that's upright and magnified. As it happens, magnified a whole lot. Magnified a whole lot. Virtual, upright, and magnified. And now I've gone through all 5 instances of the concave mirror. Now it's time to use the same ray tracing techniques to do the convex mirror. Oh God, it took so long. There's only one case for the convex mirror. Only one. Because when you flip the convex mirror over, the center of curvature and the focal distance are on the virtual side. They're not on the real side of the mirror, they're on the other side of the mirror now. And as a result, I only have one position to put my object. On the left side, the real side of the mirror. And I do very much the same rays with a small little adjustment. Here is my first ray coming in parallel. I can't say the parallel ray goes through the focus because the focus is on the other side of the mirror. What happens instead is this first ray, the parallel ray, reflects in such a way that it seems as though it came from the focus. So it's still parallel focus, but my thinking changes a little bit. A parallel ray reflects as if it came from the focus on the far side. Similarly, a ray of light that is aimed at the virtual focus on the far side of the mirror will reflect in such a way that it goes off parallel. So it's the same rule, it's just adjusting your thinking. A ray that goes toward the focus reflects parallel. And it's always true that a ray to the center comes off symmetric. So, when I view this, I have this divergent ray at the top, I have the divergent ray that came off parallel, and the divergent ray that went downward. Tracing all of those rays back, the image is always on the far side of the mirror. The image is always virtual for a convex mirror. The image is always virtual. It's upright, and it always is. And it's reduced, and it always is. Here, I have my convex mirror, and I feel certain that when I held it up, everybody got the sensation that they were in a convenience store, because this mirror is often put up in a corner, because it has a wide field of view. Now, when you look in your bathroom mirror, the person you see is the same size as you are. When you look in this mirror, the person you see is smaller, because that's the way the rays go. The image always appears smaller. As a consequence of everything in the room appearing smaller, more of the room fits on the mirror. So the mirror has a wider point of view, which makes it convenient for that. When you're on the passenger side of the car, you may see that the mirror on the passenger side has a little bit of text on the bottom that says, "Objects in mirror are closer than they appear." And the reason why is that passenger side mirror is a little bit curvaceous in order to give it a wider field of view. The consequence being that when you see an object in the mirror, its size is reduced. Your brain tries to reason out its size based on experience, and it makes a mistake because the image is reduced and your brain doesn't realize it. And so the car that you're seeing in the passenger side mirror is actually closer than it seems because the shrinking of it makes it appear further away. So it messes with your depth perception. The convex mirror. Well, you know, I kind of enjoy drawing these rays all over the place to figure out what the image is going to be and how tall it's going to be. It's fun. You draw little arrows. It's almost like a little puzzle. Thank goodness he didn't find a way to turn that into math. Well, yeah, he did. I've got an equation for that. It's called the mirror equation. F is the focal distance, where all of the parallel rays get reflected to. DO is very wisely the distance to the object. That is, from the vertex of the mirror to where the object sits. DI is the distance to the image, where the image appears along the principal axis. And the relationship kind of reminds you of the equivalent resistance and parallel relationship, doesn't it? Nature does that. It repeats patterns of algebra and calculus and physical law everywhere in the universe. This equation relates the focal distance to where you will see the image. It's very useful for figuring out where the image is going to be. But my image can also be larger or smaller or the same size. That is, my image can have a magnification. Capital M is the magnification of the image. It can be calculated two ways. Either the height of the image divided by the height of the object, and if the image height is smaller than the object height, then the magnification would be less than 1. If the image height is greater than the object height, then the magnification would be larger than 1. So the magnification is actually how many times larger or times smaller the image is than the object. But you can also calculate it according to the distance to the image and the distance to the object, but you need a negative sign. This is sort of the pesky thing about it. We want to use one equation for all mirrors, convex and concave, in all circumstances. If you want to use one equation, then you have to have a list of rules as to how you treat the numbers that go into that equation. The opposite is to have no set of rules and 5 or 6 equations. We choose to have one equation and a list of rules. The rules are like this. The object distance is positive for real objects in front of the mirror. I might have guessed that. The image distance is positive for real images in front of the mirror, but negative for virtual images. So when an image appears behind the mirror, you're calling that a negative distance. It's like there's a number line where positive numbers are that way and negative numbers are that way, and the mirror's at the origin. Positive numbers on the real side, negative numbers on the virtual side. Once you get the hang of it, you don't really need a big descriptive list. F is positive for concave mirrors, and that makes sense because the focal length of a concave mirror is on the real side. F is negative for convex mirrors, and that makes sense because for a convex mirror, the focal position is on the virtual side, the negative side of the mirror. If the magnification is greater than 0, if the magnification is a positive number, then it's an upright image. If the magnification is less than 0, then the image is inverted. Now, with these equations and those rules, I never have to draw a ray diagram again. I can just calculate the thing. But ray diagrams are really useful for visualizing what your expectation is going to be. Here's an example problem just real quick. A concave mirror. And just for fun, here on the side, I'm going to sketch out a diagram of this to sort of match my expectation. I'm going to use the equation to calculate the thing, but I'll work out my expectation. A concave mirror has a focal length of 10 centimeters. So I'm going to imagine that there's the focal position right there at 10 centimeters. The object is placed 30 centimeters in front of the mirror. So 10, 20, 30, kind of here-ish. So what is my expectation? Ray goes in and through the focus. Ray through the focus comes out parallel. Ray to the center, goes down symmetric, boom. My expectation is that I'm going to find it 10, this is another 10, I'm going to find it about 15 centimeters from the mirror, just by drawing rays. Looks like about 15 centimeters to me. Let me actually calculate it. I'll use my equation, 1 over the focal length is 10 centimeters, equals 1 over the object distance, which is 30 centimeters, plus 1 over the distance to the image, which I'm looking for. A little bit of algebraic jiggery-pokery, move this to this side of the equation. 1/10 minus 1/30 is 3/30 minus 1/30 is 2/30 is 1 over 15. So 1 over the distance to the image is 1 over 15. The distance to the image is 15 centimeters. I can see on my rapid-fire sketch that my image is going to be shorter than my object. Well, I calculate that by the image distance divided by the object distance, which is 15 divided by 30, which is less than 1. My magnification is less than 1, smaller. But the equation for magnification says the negative of the distance to the image divided by the distance of the object. The distance of the image is 15, divided by the distance of the object is 30, is 0.5. Negative 0.5 is the magnification. The negative sign implies that the image is inverted. So everything that I learned from my ray diagram, I was able to learn from my mirror equations that govern the behavior of both the convex and the concave mirrors.